about 19 of you, and hopefully we'll get a few more that'll trickle in over time. But last time we did pretty well with about 20 to 23 people. Still got the same number of people that we've got. We've got some exciting things like the James was talking about. We were talking the idea with video astronomy and live stacking. This is commercially available software for a lot less, and we have a lot of this laying around. And we're right now in the process of training some people how to do these live stackings and electronic assisted astronomy over at the observatory, so we can actually show people things at the observatory with proper distancing in place. So we haven't gotten it all done completely yet, but we're looking at doing that in the future.
Well, and the thing
we'll talk about that when we get. We'll talk about that when we get to later. I think what we're going to do now is we're going to hand this over to Coy for introductions, and then let our speaker give his presentation, and we'll sit around and
eat pizza.
All that. So, Coy.
We good to go? All right. Well, everybody, thank you so much for doing this again. If this is your first time on Zoom with us, we had a blast last time. I see some familiar faces. I'd like to go ahead and introduce my good friend, Greg Andrews. He was president of the Shreveport Astronomical Society when I was up there. He runs the Sci-Port Planetarium. He's got a great physics background. He's going to talk to us tonight about dark matter. So I know we get this question, whether it's dark matter or dark energy, anything that's in the news, people will come up and ask us about this stuff at outreach. It's one of those things that I think we need to arm ourselves with in terms of information when we go out and do outreach. So without further ado, it's Greg Andrews.
Cool. Well, salutations, everyone. I did this earlier, so I can say, live long and prosper. Oh, and I can do it with both hands too, so haha. So what I am going, as Coy mentioned, I am the manager of the planetarium here in Shreveport. I've been doing it for 16 years now. I love it, enjoy it. What I'm going to do now is share my screen. Now, like this.
All right, got it.
That's good. Now, just to let you know, so this particular PowerPoint, it has like 60-something slides. We're not going to go through all of them, okay? So there will be some that I will like skip ahead. It's not to insult anybody's intelligence, or I just assume that you know it. I just want to get to a certain point, ending point. I am not like the foremost leading expert in dark matter, mind you, but I'm always happy to answer any questions. I think for questions, I can't see the chat window or anything. I can't even see your video of you all. But if you have a question, you can put it in the chat, and then when we get to a Q&A session, I'm more than happy to answer them. Name of this presentation is The Darkness Within, Dark Matter. I love this stuff. So what is dark matter? Dark matter is a form of non-luminous matter whose presence is implied by gravitational effects. And so I want to make sure that we understand these concepts. I don't necessarily like to talk in a lot of jargon. So dark matter, by non-luminous, it means it's undetectable. It produces no light or does not interact with light. It doesn't make a sound. Of course, there's no sound in space. There is no smell to it. There's no taste, and there's no physical or tactile sensation. So in essence, it's something that is truly undetectable by direct means. But we know that it is there because of indirect methods. And so we refer to this as the missing mass problem. I put the joke in there, hopefully you'll get it. I heard that there was a petition to call it dark gravity, but it didn't have enough pull. Haha. Okay. So when it comes to dark matter, let's do a little bit of history. Starting with Mr. Jan Oort. And one of the things that he's famous for is he studied, hold on, let me, laser pointer, okay, haha. He studied the Milky Way galaxy, and he was monitoring the stars within the Milky Way galaxy. One of the cool things that he did through this study is he was able to prove that our solar system is not at the center of our universe, or excuse me, at the center of our Milky Way galaxy. That was one of those things, those concepts that people wanted to hold on to. We are at the, first, we're at the center of the solar system. Nope, we're not. Well, we're at the center of our Milky Way galaxy. Nope, we're not. So he proved that we're not. He's also famous for theorizing what we call the Oort cloud, or in other words, the home of the comets. But what's also fascinating is that in 1932, through his studies, he showed that stars within our Milky Way galaxy have a similar orbital velocity, despite their location. And we're going to talk about this a little bit more later on, though. But essentially, it says that stars in this area and stars way out here all have the same orbital speed. And that was something that was a very big moment. But this guy, Dr. Fritz Zwicky, is the one that's kind of labeled as the father of dark matter, right? So first of all, he coined the word supernova, which is something I found that was kind of cool. One of the most explosive events to occur in our universe, and he developed a name for it. He also developed the theory that a neutron star forms after a supernova. Yes, if you notice in his picture, he says, "I deserve a bigger image." I'll tell you why I kept his image small. But as I mentioned, he's the father of dark matter, and then I'm trying to say kinda. So he came up with the phrase for this, but he was not the first person to actually question or present this idea that there's something out there in our universe that it's there, but we can't directly detect it. It's almost like how Nicholas Copernicus, right? Nicholas Copernicus comes out and says, "Hey, the sun is at the center." And so nowadays we sort of call him the father of heliocentrism. But there were some other people before Nicholas Copernicus that actually presented this idea of, hey, putting the sun at the center of our solar system. So that's why I say he's the father of dark matter. When you look at most of the context, they always said you starts with him, but he was not sort of the very first one. In 1933, Dr. Zwicky was studying what's called the Coma cluster. The Coma cluster is actually out tonight, of course, as fellow amateur astronomers, you're aware of this. And he was measuring the movements within these galaxies. And he realized that based on how these galaxies were moving around, the galaxy shouldn't exist, right? That this galaxy cluster, and there are over 1,000 galaxies in this cluster. Let me just point this out. The main galaxies you see are the big sort of fuzzy dots right there, but then they have those tiny small dots right there, small dots right there, small ones right there, right there. Those are galaxies there as well. So it's really cool. I love this picture. So he's looking at all these galaxies and he's realizing that they are moving around at an incredibly fast speed. So fast that this galaxy should again have dispersed. It should not be here, but yet it is. And what he comes up then, and then he does something which is kind of cool. He takes measurements using Newton's laws to determine the mass of the cluster. And then he comes back and he compares that to a mass that he finds by basically measuring the amount of luminous matter. And these two methods are independent of each other. But when he compares the numbers, he realizes that according to Newton's law, there is about 400 times more mass or matter that should be here than what he's seen. And so this was too large of a discrepancy to ignore. So he did carry out some more observations. Then he realized, hey, you know what? This keeps coming up. And so he said that there must be missing mass. But unfortunately, this is why I said he has a small picture. This last bullet point, Dr. Zwicky was very famous because he was very contemptuous towards astronomers. One of my professors in college actually worked with him during her undergrad, and he was famous for saying the phrase "spherical bastards" when it came to other astronomers. So if you were not part of his clique, basically he looked down on you, right? So he had a bad reputation, if you will, but really smart guy. Later on, in 1975, Dr. Vera Rubin made a shocking announcement, and that is she agreed with Dr. Zwicky's proposal of missing mass, and she introduced what is called the galactic rotation curve problem. And we're going to talk about this a little bit later on, but just to introduce you to you, basically she goes and she studies these spiral galaxies. And she realizes that the stars within this spiral galaxy all have more or less the same orbital speed. So based off that concept, there has to be something that is holding these stars in place, some type of mass, if you will. And I love this picture right here because this shows a study by somebody I can't remember, but that little tiny fuzzy wuzzy dot in the middle, that's actually showing our Milky Way galaxy, right? Saying this is our Milky Way galaxy that we can see. But based off what you call the presence of dark matter or these movements that we see, this is the amount of stuff that we should actually be able to detect directly. So this is what we see, but mathematically, this is what should be present, okay? So she comes up with this and she says, hey, this is something interesting. Dr. Zwiski's results were based on galaxy clusters. So looking at thousands of galaxies moving around and saying, yep, there's dark matter there. Dr. Vera Rubin's results were based on individual galaxies. And so what this comes to support is that this extra gravity, thus this extra matter, is lurking in galaxies and the space between galaxies. I oftentimes use an empty box analogy. And what I mean by that is, let's say you have a box that's completely empty, right? So you put a box completely empty and then pretend as if you were trying to lift it, right? So don't want to strain your back, but imagine like it's super heavy as you try to lift it. And then have somebody come over there and look and say, hey, do you see anything in the box, right? No, you do not see anything in the box. But when you try to lift it, it's super duper heavy. And this is literally like dark matter, right? We can look and we can say the box is empty. But when we look at trying to move it or trying to lift the box, it's super duper heavy. And to me, that would pique my curiosity, right? Like, how is a box completely empty, but yet weighing so much? And this is, again, along the same lines of what dark matter works at or operates as. So this is going to do a little cool physics reviews. I don't know if anybody's seen the movie Madagascar, but this is King Julian over here. Sings that very famous song, I Like to Move It, Move It. I'm not going to play it in the background, but you know, it's a cool song. I love it. So making things move and why we blame gravity / mass / matter. So a force is a push or pull, okay? And there are 4 fundamental forces in our universe at play. The first one we're going to name out is a strong force. And it's incredibly strong, but it operates only on the atomic level. Once you go beyond the atomic level, it's no longer relevant. You also have what's called the weak force, which is incredibly weak, but it operates.
We lost audio.
Yeah, I don't know what happened to Mr. Matthews.
Well, I just came in. I hope I didn't kick him out.
Yeah, it said that I was unmuted, but now I'm unmuted. So hopefully everybody can hear me again.
I got you back.
All right.
I got you.
Cool.
Yep.
Super. Thank you. So force, again, strong force, incredibly strong, but operates only on the atomic level. Weak force, incredibly weak, but it operates, again, only on the atomic level. And then you have something called the electromagnetic force. And this is force is a weird phrase. It's weaker than strong, but stronger than weak. I feel like that's like a campaign slogan or something. I don't know, but I like that. But it's weaker than strong force, but it's stronger than the weak force. It operates on all particles beyond the atom, and it's based on the electric fields. But the cool thing is that it is independent of mass. And down here, I kind of gave a way to view this. So the resting mass of a proton is almost 2,000 times the mass of an electron, okay? So you put them on a scale, so to speak, the proton's going to weigh almost 2,000 times more than an electron. But yet, the electric charge of each one is the same. So hence, this helps to prove that the electromagnetic force is independent of mass. So that comes down to, last but not least, it comes down to gravitational force. And this is the weakest of all forces, but it operates on all particles beyond the atom that have mass, and it is dependent upon mass as well. So that's the key phrase to it, that this particular force is dependent upon mass. Let's do like this. Oh, there it is. Okay, so when we look at trying to describe dark matter, remember this stuff is out there, it's doing this weird stuff. It can't be strong force, it can't be weak force, it can't be electromagnetic force. So the only thing that is left over is using the laws of gravity to describe it. So how do we detect this stuff, right? And there's multiple ways, but I'm just doing this again to the summary way. When you find a galaxy, and then you measure the brightness of this galaxy. Because it's a star, you assume that if one star weighs so much or has so much mass, then you can guesstimate the number of stars in the galaxy that are required to produce that brightness. And then you do some abracadabra math, and you get the mass of the galaxy. So for example, this is looking at the Andromeda galaxy. What you do is you find a single star right here, and you say how bright or how dim is that. You can infer its mass, and then from there you say, well, how many stars like this would it take to produce a galaxy that is this bright? And then you can do the math, and then after you find that mass, you can find the galaxy mass. And I kind of have a simplified version of this equation down here. Okay, so you divide the galaxy brightness by the brightness of the individual star, and then you multiply it by the number of stars in the galaxy, and you get the mass. The next way is basically, oh, this is something I'm not going to worry about. This is talking about galaxy clusters. I'm not going to worry about that yet. The next way is, and I love this quote, you don't know the power of the dark side, right? The next way is to use Newton's law. The parts, I don't know if you have color on the screen, but the parts that I have highlighted in yellow are basically the main context of this particular slide. There's a basic formula, hopefully we recall it, F equals ma. So force equals to mass times acceleration. And what I love about this is this second part right here. If you have mass, then you have a gravitational pull, right? And vice versa. So any particle, any object in our universe, if it has mass, or the property of mass, then we know that it can exert a force, and in this case, a gravitational pull. And the thing I want to realize is that this is proportional. So as the mass of an object increases, its gravitational force increases as well. And so what this means that gravity and therefore mass can make objects move when these objects are separated by an appropriate distance. Okay? So all of this comes together, and like I said, this is the main equation I want to worry about. I'm not going to worry about this one. This is really cool, but I'm not going to worry about that. But this is the main thing right here. If you have mass, you have gravity, and if you have gravity, you have mass. Gravity makes things move, okay? So if we see some type of movement going on, then we can infer that there is a mass that's operating, that is causing this movement. And so one type of movement is something that's called escape velocity. And just sort of to rehash, oftentimes we think what goes up must come down. And for the most part, that's true. But we see rocket ships. Rocket ships go up off the ground and they don't come back down. So they can escape the surface of Earth. And so escape velocity is the necessary speed to escape from an object and not fall back toward it. An example I'll use is if you have a ball. You take a ball, you toss it up, and then it'll come back down to the ground, right? If you throw it even harder, it'll go up even further, but then eventually it's come back down to the ground. But if you have superpowers and you throw that ball super duper duper fast, that ball will leave away from Earth and it won't fall back down. So you have thus achieved escape velocity. And what happens is we have this equation right here that we use. And again, I'm not trying to go into the intricacies of it, but I just want to introduce it to you all. And so you look at this equation right here, and what it does is you can basically rewrite it to this to show that this is how you can calculate the escape velocity. So you look at 2 is the number 2, g is a gravitational constant, and this doesn't change. M is the mass of an object, and then R is the radius or the distance between the two objects, okay? Or you can also rewrite it like this, and this is the key one, where you have gravitational constant, which is always the same, the velocity and the stays the same for the most part, and the R stays the same. So you get these equations and you apply them, okay? I have this little, let's see if it'll do it for me. It doesn't want to, let me see if I exit out the laser pointer. Here it is. And so escape velocity can also be used in what I call the merry-go-rounds scenario. So this little video right here, the dude was holding gun, right? But if you notice, this merry-go-round goes so fast that he can no longer hold on. So he has escaped from the merry-go-round. So that moment right there, where he reaches a certain speed that he can no longer hold on, that is escape velocity. So that's a very important rule of thumb to use when discovering dark matter. This slide just shows that all of these equations are interactive with one another, but let's apply this. So let's start off with the planets, right? The principle is the farther out that a planet is from the sun, the slower it goes around the sun. So I'm not going to quiz anybody, but we all know that Mercury takes 88 days to go once around the sun, right? And then Venus takes what, 246 days, Earth takes 365 days, Mars takes almost a little over 2 years, and then so on and so forth. And so what happens is the farther out that you move from the common point of orbit, the longer it's going to take you to go around something. And so this makes sense. So this is how the graph would look, okay? So this is what we see with our planets. The farther out that they are, the slower or the longer that it takes to go around the sun. So Dr. Vera Rubin studied the Andromeda Galaxy. This is a picture actually by a good friend of mine, Jody Rainey, Coy, you may remember him. And so he took this picture a couple of years ago, and I love this picture. So he takes a picture, so she's looking at the stars. What she's doing is she's looking at these stars here, then looking at the stars here, and then looking at the stars farther out. And all she's doing is picking a star and then measuring how fast it goes around, okay? And again, the principle applies. The farther out that you are from the center of this galaxy, the faster you're going to go, the slower you're going to go around this galaxy. So if you're way out here, you're going to take just a colossal amount of time to go around versus a star that's closer to the center. So this sort of breaks it down. This graph right here is something that I use frequently. Unfortunately, I can't get rid of that B line, okay? So ignore that B line. But this is, the dashed line is what I want to focus on, okay? And so this is showing that stars that are very close to the center will have a very high velocity. So stars in this area will have a very high velocity. And then again, following the laws of physics, that when you get the stars in the red area, that their velocity or their orbits will go slower and slower. So these will go around really fast. These will go around, but not as fast. And then these stars right here in the outer rims and fringes will not go around as fast. So it just basically slows down the velocity. And this is what Dr. Rubin discovered. She looked at all these stars within that galaxy, and she realized that their orbital speeds are pretty much the same, okay? And she did this test 14 times. There's the graph right there. 14 times that she went and measured the orbital velocities of stars within here, and they all consistently produced the same results. That is that all these stars are going around at roughly the same speed. The only way to explain that then is that all these stars have to be in the same small area, okay? So let's go back to here, to the planets, right? So if I'm measuring the orbital speeds of Uranus, Neptune, or whatever, and they all have the same speed as Mercury, then that assumes that they all are near the center or very close to the sun, but they're not. So here, again, this is what should have been expected. There should have been a drop off. The stars here are super fast, going around the center super fast. These go around here fast, and then these go around here slower. So the velocity gets slower as you get further away. What she saw, basically, that all the stars were going around at the same rate. And so the only way that makes sense is that, again, all these stars are in the middle of something that's very, very huge. The problem is you can't see it. When we look at the Andromeda Galaxy, this is what we see. So what else is out there? And that's what we call dark matter. She did this not only for the Andromeda Galaxy, but she also did this in other galaxies, and she's had the same results. That all these stars, they should have been, the stars near the galaxy should be fast, and then as you go away from the center, the velocity should be down here. So the graph should be slanting down like that. That's not what she observed. She observed stars that, even though they were really far away from on the outer fringes of these galaxies, they were still going around just as fast as stars that were very close to the center. So this lets you know that these stars are, that there's something holding them there, and that something is gravity, okay? But as we talked about before, gravity comes from the presence of mass. So if you have gravitational influence, you have mass. So we can see the effects of gravity, we don't see the mass. And so that's what we call the missing mass, or you can say matter as well. Not saying that they're all interchangeable, but that's another topic for another day. What I do like about this is, and I made sure to put this on here, that some of these stars should have escaped. So going back to here, not the Andromeda exactly, but some stars that she found way out here, they should have long since flown off. Going back to that merry-go-round analogy, okay? You're holding, you're like me with my uncles. I go to the park with them when I was younger. They put me in a merry-go-round, and they swing the merry-go-round. At some point in time, it goes so fast I cannot hold on, right? That's what's going on with stars way out here. These stars should not be there, but yet they are there. Something is holding them. So let's get back to the Coma cluster. So here's a picture of the Coma cluster, and we apply the same principles, right? So we look at these galaxies that are on the outskirts, and what happens is, out here in the outer fringes of this galaxy cluster, these galaxies that are out here, they should have long ago have left this cluster. Why? Because they exceed the escape velocity, but yet they are still there. These galaxies are being confined that are way out here in the outskirts. They're being confined to this cluster. So how can they be there unless gravity is holding them? So gravitational force is holding this cluster in place. So you look and see, this is the amount of stuff that we detect, the amount of matter that we detect. This is what you call luminous. This is what we can actually see. But based off the actual mathematical calculations, this is what we should actually be seeing. That is a huge discrepancy. So these galaxies exist in this area right here. Now, again, this is all we see when we look in this area. This is all that our eyes, our instruments can detect. But when we do the math and we say how you move, and based on how you move, we can infer the mass, this is the amount of stuff that we should be actually detecting directly. The problem is we don't see it. It's empty. And that is, again, the presence of dark matter. Here's another one. So this is a combination of a galaxy along with a cloud, if you will, or a gas, rather. So the white dots are representing galaxies within this cluster. The purple haze is showing X-ray gas. They measure the temperature of this X-ray gas, and this X-ray gas is incredibly hot. It is so hot that it should have boiled itself away, but yet it's still there. So something is containing it, and that something is the force of gravity. But remember, if you have a gravitational force, you have to have a mass. So we can see the effects of the gravitational force, but we don't see anything that is able to say, yep, that's the actual source of it. So that's why we call it dark matter. The bullet cluster was one I remember being in college, and they talked about this. So this was actually a collision of galaxies. So here these galaxies collided with each other, and based on how this collision occurred, it showed the presence of dark matter. So what happens is when this collision occurred, the galaxy clusters stayed in place, okay? And somehow the clusters, the galaxies themselves became separated from the gas cloud. So how did this happen? It's because of the properties of dark matter. Now, I love this right here because what we discover something, right? It's totally amazing. And that is that dark matter is collisionless, right? So this particular galaxy had dark matter keeping it together. This galaxy had dark matter keeping it together. They collided, but there was no way, no type of detection. There was no type of energy spike that said, hey, this collision is happening. So it shows that dark matter is collisionless, and it does not interact with itself, at least that we know of. There was a question, I was sitting in a session about this, and it said something prevented the gas from traveling with the dark matter. What was it? We don't know. Another way that we detect dark matter is through something called gravitational lensing. This is super cool, thanks to Einstein. So gravitational lensing, basically it shows that the force of gravity can bend light, and just like a black hole. The amount of the bending of the light is based on the strength of the gravitational force. So the stronger the gravitational force is, the more the light is bent. And what this allows us to do then, remember, as I said before, more mass means more gravity. So if I see more of a bend, that means that I have more of a gravitational force, which means I have more mass. And what we're able to do is look and see that light from a galaxy is being bent. What's happening is, let's go back to this analog. So here's Earth right here. Here's an actual object that's behind the sun. But because the light from this star gets bent, instead of it making a true direct path straight to Earth, it gets bent and curved. And that allows us to see behind this sun. And we can do that same thing with these galaxies. When we look at this galaxy cluster right here, this galaxy cluster, remember, it has a lot of mass. Galaxies have a lot of mass. And so what that means then, that they can bend light. And so this galaxy is actually behind this main cluster of galaxies in the foreground, okay? So this is the background galaxy. We shouldn't be able to see it. But the reason why we're able to see this is because light is being bent from this cluster, and then it directs the light to our eyes. But instead of it being a point-like object, we see smears, and that's something neither here nor there. But this bending of light can cause what's called a gravitational lens, is what this is. It's something that Einstein actually theorized. And we can see this happening, right? And so what we realize is that some of these galaxies that we're seeing, so the bright object is the main galaxy, and that's, we can actually see directly. And then that smear around these galaxies, that sort of cloudy ring, that is actually a galaxy that's in the background. We don't see it directly, but we see it because the light from that galaxy is being bent around to our line of sight. And so some of this lensing, the reason why it's able to do it is because of dark matter. Again, we can measure the amount of this bending of light, and then we compare that to the galaxy we see. And we say, nope, so for example, this galaxy right here, just by itself, should not be able to bend and cause this type of gravitational lensing. So it has some extra help. It has an extra gravitational force influence in it. Well, where's that gravitational influence coming from? It's coming from dark matter. Remember, you can't see dark matter, but you know it's there because of the presence of its gravitational influence on objects in our universe. And so we see this lensing effect happening all the time. I said in a seminar where the guy was studying this, there's something called microlensing. I'm not going to get into that, but lensing is also another crucial way that we can detect dark matter. And so this allows us to find out where dark matter is. So does it exist only on the outer edges or of a galaxy, or maybe it's only in the center of a galaxy, or maybe it's just in galaxy clusters? And what we have learned is that dark matter is everywhere, okay? So just to rehash it, I don't think I explained this, that we call this dark matter, again, dark because we can't see it or detect it directly. And then it's matter because, as I mentioned before, when it comes to F equals ma, if you have a gravitational strength, then you have mass. Well, mass and matter can kind of be interchanged, not all the time, but kind of. That's why I say I prefer the presence of, I prefer the name dark gravity, but dark matter is what Mr. Zwicky came up with, and that's what it is. So what we're able to again show is that this dark matter is everywhere in our, not just in our galaxy, but in entire clusters of galaxies, and it permeates the universe as well. And this includes being found under your nose. I had somebody ask me a question, well, you know, is it in my nose, under my nose? Yes, ma'am. Yes, sir, it is under your nose. But the cool thing is dark matter doesn't care about you. It only affects galaxies and clusters of galaxies. And so when we look at the composition of our universe, visible, we realize there's more stuff out there than what we can see. Visible matter makes up 4%, dark matter makes up roughly 23%, and dark energy makes up 73%. And so what this shows is we basically know a small amount about our universe. Everything else is just not guesswork, it's there. We just don't know anything about it because it does not interact. It does not give us any information directly. Again, no smell, no touch, no sound, no visible light, so you can't see it, but it's there because of how it influences things. And so I love this is because this is something that might be for a whole other topic, but we realize that the presence of dark matter is the reason why we have galaxies today. When you look at the structure of our universe, we know you get a whole bunch of stars together to form galaxies, then a whole bunch of galaxies together to form clusters, then a whole bunch of clusters together to form what we call superclusters. But to start all this, everything had to come together. When you talk about the process of a star is created because of the effects of gravity, okay? But our universe could not exist today unless dark matter helped make it possible. So dark matter wasn't something that just kind of came onto the scene in our universe, so to speak. It was there from the very beginning. It helped to create the universe as we know it now. And what this leads us to is this sort of universal matrimony. What we realize is where you have dark matter, where we detect dark matter, there is visible matter. In other words, there are galaxies there. And when we don't see any dark matter, we don't really find any galaxies. And it might be hard to tell in this video, I hope it's coming through correctly, but this looks like a cosmic web, right? Like a spider web, right? So imagine you have a spider web, and where you see the thread, the strings of the spider web, that's where you would see actual matter, actual galaxies being formed, or at least located along those filaments or along those strings. And then the spaces in between the strings, there isn't anything there. So those are what we call voids, okay? So I'm calling it strings because I'm, again, comparing it to cobwebs, but this was traditionally known as filaments, right? So these filaments are just these stretches of material, of dark matter, like a string of dark matter. But these are huge, okay? These contain galaxies. In this video, where you see that white stuff, right there and right there, that white stuff is actually representing visible matter, the stuff we can see, and all the purple stuff is representing dark matter. We can't see it, but we know it's there because of how it pushes and pulls and makes galaxies move in our universe. And so again, dark matter operates on a large scale. It operates on stars to a degree because they're part of galaxies. It operates on galaxies individually. It operates on clusters of galaxies, but it doesn't operate on planets. So that's something that's just one of I know we might take that for granted, but that's actually a property of it though, right? So we have to find out, why does it not operate on planets, but it operates on everything else beyond planets? So We don't know. This image is called the Hubble Ultra Deep Field image. It actually shows signs of dark matter. I'm not going to get into it. I love this image. I'm pretty sure as amateur astronomers, you all have heard of this, but I love this. 10,000 galaxies that just told us so much about our universe, made us rethink and literally redefine what we know about the universe. This is that picture that I mentioned again. When it comes to our Milky Way galaxy, this is the amount of stuff that we can see, okay? So how we were able to do this is we look at stars that are on the outskirts, on the outer edges, and we actually have what are called dwarf galaxies, small galaxies. You may think of these as the small Magellanic Cloud, the large Magellanic Clouds. So we can look at things that are going in and around our Milky Way galaxy. And we realize these things are zooming around at an incredible rate or an incredible speed. They should not be present. They should have been way over here, some off the screen, but yet they are still there. The only way that they can be there is something is holding them. That something is gravity. And again, that gravity then, the source of gravity, as we know it, has to come from mass. So dark matter is what is also, again, permeating our own Milky Way galaxy. So what is it? We're still in the guessworks about this. Some really cool stuff, something called MACHOs, massive compact halo objects. And these are basically huge chunks of invisible stuff, to quote, drifting out in space. You think some people try to say they're remnants from primordial stars, so stars that first occurred, generated, in the very first stages of our universe. Some say neutron stars. Maybe it's a big planet. We don't know. This is more or less being disproven, but we're still trying to hang on to it. Something else, the two leading theories are there, what you call WIMPs or axions. WIMP is a weakly interactive massive particle. And these are particles that are ginormous, right? They are, in terms of hydrogen, they weigh more than a lead atom, okay? So these are very heavy particles, but they don't interact with anything. And that's kind of weird, right? That's like having again, the box, right? Again, a box that is empty. You see it's empty, but yet it is super heavy to move, right? How is that possible? So WIMPs provides a better way of doing that. Axions are also another leading theory. We have these are seriously small particles, like super duper duper tiny. And they scatter due to magnetic fields. And this scattering should produce certain radio frequencies that would allow us to detect them. And if we can detect this certain radio frequency, then we can really say, yes, axions exist. So these two are just theoretical, okay? We have not directly detected them. But what we can detect is maybe the results of them, okay? I say it's almost like if you have a child, right? Your child is not you or the other spouse, right? Or you or the mom or the dad, respectively, but that child has traits of you. Okay, so they kind of look like mom, they kind of look like dad. And that's kind of what happens here. So we can't detect these directly, at least we haven't yet, but we are looking to detect them indirectly by looking at some other particles that may have been produced from a WIMP or axion. Other possibilities, neutrinos, this is it right here. And then you have something called cold dark matter particles, hot dark matter particles, warm dark matter particles. The reason why we get into particles, because when you look at our universe, everything is made up of something, right? So like an atom, right? When you break anything down to the most indivisible part, it's supposed to be an atom, okay? So when we look at everything in our universe, everything is made up of something. And so we have to figure out what is dark matter made up of. Well, it has to be a particle because that aligns with everything else that we know of in our universe. So what type of particle it is what we are still trying to figure out. There was something that was called MOND, Modified Newtonian Dynamics, that was coming out. A lot of people were like, oh, wow, but it's been nullified, but still has some people like that. So going back to that empty box, again, the box is still empty, right? But we are also understanding that empty is not really empty in the way that we like to think of it. There's some other theories that are out there and some more studies going on. That's going to be something else. I'm going to give some closing credits here. Hubble Space Telescope, the Cosmology short course is something that's really cool. These different things. I had Vincent van Gogh because I think one time I used a picture. Oh, I love this picture right here. I got the chance I was talking about seminars, so a variety of different seminars that I sat in. There's me right there. And then this guy right here, that is Michael Turner. Okay, so if you, Dr. Michael Turner, if you were into cosmology, he's the one that actually came up with what you call cold dark matter. He's actually the part of the team of people that came up with the phrase dark energy as well. So it's really cool. And Dr. Kolb is not in here, and Dr. Cizeli, I don't see him either. But anyways, so it's just some really cool people. With that, Donna said, I'm going to go ahead and end it there. So thank you all so much for coming, or I can't say coming, but for listening in. I am going to end my screen sharing at this point. If you have any questions, by all means, please feel free to let me know.
Greg, first off, I want to say you have been probably one of the most engaging and delightful to listen to speakers we've had in a long, long time.
Yeah.
Okay, congratulations to you.
Amen.
Thank
Yeah,
you.
yeah, bravo.
Yeah.
Thank you. So, oh, I didn't show some that signed in early. I was talking about how I got my Darth Vader shirt. So I got to really go to it. So thank you for that. I appreciate that compliment.
Is he your father?
I want to say yes. My actual dad might have an issue with that. Like, hold up, let me talk to my mom. But by all means, he is definitely my father into physics for sure. Yes.
Greg, question for you. This is Marvin Point. I used to be president of the club here and was very active, but I haven't been for a while. What's your background? Sounds like you've got some good education.
Oh, yeah, thank you. I just study a lot. So my degrees, I went to LSUS, LSUS here, and my degree is in physics, and I have a minor in mathematics and robotics. How I really wanted to do astrophysics, but they did not have that program here. So I stuck with physics. Thankfully, one of my professors I mentioned before, she was actually an astrophysicist. So she basically took me under her wing. And I was just like enthralled at everything that I was learning underneath her. And it completely fascinated me, right? Like when you realize it, astronomy is a science that we can't study directly, right? So you have to know the concepts, you have to know the principles, you have to know the science, you have to know the math, or at least the math is, please don't ask me to write out Schrodinger's equation. I can't do that, right? But I know the concepts of it, right? And yes, I think the cat is dead, but only if you think it's alive. And if you think it's alive, then I think it's dead. So having said that, so having said that, I got my degree there. I was actually getting ready to go to Rice University as part of a MD PhD program for the astrophysics program there. But I found out that here in Shreveport, there was a planetarium that was being added onto the local science center. And I said, well, hey, I applied for it and they accepted me. And I was just like, wow, truly amazing. So that helped me to merge this love and passion that I have for astronomy and physics to the general public. And yes, sir. And so just ever since then, I tell people I am a nerd. I'm a good-looking nerd, like we all are good-looking nerds here, right? So, and it was just something I fell in love with it, start studying it, and I want to be able to explain it in a way that people can understand it. And working at Sci-Port definitely twist your arm to make sure you do that.
Well, it sounds like from the way you talk that dark matter is actually something that is matter, as opposed to,
to mass,
some kind of mass that we can't see. It's not like gravity, where gravity is there and we can't see it. Why isn't this dark matter something like gravity that we can't see, but it is clearly there, rather than actually being a mass or a substance?
Yes, sir. It's a great question. So I mentioned this briefly just to explain that when it comes to matter versus mass, right? Like there's this battling of questions. What is matter? Matter is a property of mass. Well, what is mass? Mass is a property of matter. So it goes back and forth like that. So I try not to use them interchangeably. So if I cause confusion, I do apologize. The reason why we call it mass or matter is because we look at, it comes down to what property do you have, okay? And the property that we can actually detect is gravity, okay? So gravity is in fact a property. And again, not gonna get into it, but in you all's neck of the woods down there, the not LIGO detected gravitational waves, but thinking of something else, but they discovered the Higgs boson, okay? And so the Higgs boson gives the property of mass. Having said that, when we look at how things move in our universe, that movement is due to gravitational forces. I kind of explained that there are 4 forces. Gravity is the only one that makes sense. Well, how do you get the attribute or the property of gravity? That comes through mass. So in order to have a gravitational influence or gravity, you have to have mass, right? This is why light around us does not weigh on us, because it does not have a mass-like property. So that's why we know within the context of our understanding that about our universe, dark matter does have a property that is mass. Now, how it interacts is what we don't know. So hopefully that answers your question.
That sounds fine to me.
So I get excited about this stuff. I get loquacious and like,
That's fine. It's that excitement's what I'm enjoying about your talks, man. It's just, I like you. You can come around more often.
Thank you. Thank you. Oh man.
Hey, Greg, tonight, for whatever reason, this is the first time this has ever occurred to me, but I'm seeing it now as also a medium that light can travel through. I mean, you talk about it's not interacting, but now I'm seeing it not only as matter, but a medium like water or instead of the vacuum of space. So I'm seeing dark matter as something that light can travel through.
Yes, sir. And one of the, when I did this a long time ago, unfortunately I took the slide out, but I basically said that dark matter is the ether of the universe. And there was somebody who was like, really? Ether doesn't exist. So yeah. But see, and that right there, that observation proves another example, right? The fact that light can travel through it. So it doesn't interact with light. Because if it did, it would make the light disperse or something like that. So yeah. So it's like I said, we look at the box, we know it's empty, but what can we tell about the emptiness though? Yes, sir.
Ether might just be the right thing to say. I mean, we're going to everybody has been poo-pooing ether since the 1700s, and now we're going to say, all right, it's back.
Yes, sir. But then you have to account for dark energy. And dark energy might be a little bit jealous of that, though. But yes, sir.
What is your best guess as to what dark energy is?
Oh, wow. I wasn't expecting that. So no, I can only go based on, I'm sort of the old school physicist. And what I mean by that is I like to test things, right? Like it's great to have a theory, but you have to have the observations and therefore the experiments to back up your theories, okay? So the best thing that I can see though with it is, because it's practically undetestable, is that it is virtual particles, right? That's the best explanation that I've heard, that are popping in and out of existence. I don't know where these particles would come from, because why am I referring to particles? Again, when it comes to the structure of our universe and anything, everything is made up of something. So that you have to have a building block. And therefore we just normally assign it and call it a particle, okay? To me, it would be a virtual, it's the essence of space is one way I've heard described it as, but the best way I can think of it, it's a virtual particle. I'm not saying it comes from another universe or a parallel universe, although mathematically speaking, a parallel universe makes the best sense. It answers questions not only for dark energy, but also dark matter as well. The issue, of course, is you can't test it. So to stay within the confines of our own universe. I'm saying it's a virtual particle. It's something that's just the essence of our actual universe.
Well, is the concept dark energy and dark mass or dark matter the same or different?
Great question. They are actually different. Dark matter pulls everything together. So as I mentioned before, it operates based off gravitational forces, and gravity is always an attracting forces. So it pulls stuff together. Dark energy is the opposite. I'm not saying it's anti-gravity, although some people like to say that. And what dark energy does, it expands stuff. But how it operates is different. Remember, dark matter that we know of operates on galaxies and clusters of galaxies, and then clusters of galaxies, what we call superclusters. Dark energy basically operates where matter does not exist. Okay, so I want to share my screen again so I can show you in this presentation the PowerPoint right here. Come on. This image right here, right? So I talked about how where you see the white stuff, that is visible matter, okay? And then the purple stuff is representing dark matter. So everywhere you see this purple stuff, that's where we see matter actually being formed or being located or placed in, okay?
Everything else is
Dark, but what about the space in between, okay? So the space that's in between, like you can sort of see these dark patches here and there, those dark patches. So the space in between is empty. So in there is where you see dark energy really taking its place. So where there is matter, there is not dark energy. But when there is no matter there, so nothing, whether visible or non-visible matter, that's where you find dark energy. Okay. Uh-oh, it closed on me. But hold on. It stopped sharing my screen, but let me show you this picture right here. Let me get it up.
Well, you're doing a fine job of bringing us all to the dark side.
Well, then I am doing my job, sir. Let me do. There's a picture that I grabbed it recently because I was talking to somebody. Where are you at? Give me just a, nope, not right there. And I think, so please just bear with me. I'm trying to find this picture. It basically helps to show the structure that I keep talking about and referring to. Oh, okay, here it is. So let me bring up this picture first. And unfortunately, my computer moves just a little bit slower than I would like it to when trying to bring up images. And it's a Windows thing, I know, right? And sometimes I'm like, I should be a Mac user, but I'm too in love with Microsoft Windows. Okay, let me share this if you don't mind. To be able to answer your question. Okay, so hopefully everybody can see this particular image right here. Where you see this white stuff right here, that's where we find galaxies at. And that's also where we find dark matter. But remember, dark matter is basically outnumbering this. So for every one particle of visible matter, there is an average 6 dark matter particles that are influencing it. There are some places in our universe is a little bit more, a little bit less, but that's an average. But look about this right here. This is called the Boötes void. And so in here, we find galaxies in this area, in this area, in this area. So we're looking at these galaxies, right? But in this area, nothing. It's very, very sparse. So in this area right here, dark energy takes over big time, okay? So that's the difference between dark matter and dark energy. Dark energy operates on space itself, and it causes space to actually expand. Dark matter operates on matter, the stuff inside of space or inside of our universe, and it causes objects or things to come together, though. Okay?
Let me get this straight.
Yes, sir.
Neither dark matter nor dark energy are actually detectable, correct?
Correct. They are not directly detectable.
Do you know that they actually exist?
Because the evidence. Let me give you an example.
The conjecture, yes, but evidence?
Yes,
What
sir.
evidence?
It's the evidence, right? Let me give you an example first. I'm going to use me as an example, okay? So I'm back in my younger days. Let's say my mom baked some cookies, okay? I'm saying hypothetically because thankfully nobody really knows my mom. My mom really can't cook, okay? So I'm just saying. So that's why I said hypothetically. Okay, so hypothetically, she baked some cookies. I know, right? So don't tell her, please don't tell her. Okay, so hypothetically, she bakes some cookies, and then she tells me, Greg, don't eat any cookies. I'm like, yes, Mom, I'm not gonna eat any cookies. She walks out the kitchen, and what do? I go eat those cookies. She comes back into the kitchen, and she knows that the cookies are gone. And she says, Greg, did you eat the cookies? My reply is going to be, no, I did not eat the cookies, right? I know you all are perfectly well-behaved angels growing up. I kind of had some quirks, right? I blame it on my brother. For the record, I am an identical twin, so I like to blame him for stuff. So I say I didn't eat the cookies. She says, okay, hold out your hands. I hold out my hands. I have cookie crumbs on my hands. She says, open your mouth. Open my mouth. I got cookie crumbs in my mouth. So although I might say I didn't eat the cookies, the evidence clearly says I ate the cookies. Okay. So
Granted.
Yes, sir. So going back,
But that is a little rebuttal here. You
yeah.
have physical evidence there.
Yes.
There is no physical evidence for
Yes,
dark matter or dark energy. They're undetectable by definition.
Which is why we call it dark as well, because in fact they are not directly detectable.
Call it purple.
It's just I wasn't around when they named it, but yes. But having said that, you can get things indirectly. So let me give you another example. Let's say you put your hand on a door and that door is extremely hot. That will tell you that there is a fire behind that door for the most part, right? So you might not smell the smoke. You might not see anything, but indirectly, you know, based off your information growing up, sir, that there is a fire behind that door. So it's indirect evidence that we are relying upon. And if it was just anything, whatever, we would be like, whatever, dismiss it. But we are relying upon the principles of physics. And when you look at those principles of physics, we've been doing pretty well with them, right? Not saying we know everything. You know, we're always looking for the next thing. That's why there was something I mentioned in the presentation. It's called MOND, which stands for Modified Newtonian Dynamics. Somebody that said, you know what dark matter is, and to a degree what dark energy is, it's just we have the wrong approach of examining gravity. That gravity is not uniform in our universe, that there are pockets in our universe that says that the property of gravity changes somewhat. And we try, and that was actually gaining a lot of threshold, because MOND theory actually answered a lot of the questions that related to, I think it's either individual clusters, the galaxy rotation curve. Remember how I said that curve is basically flat? So it shows that all those stars that are going around the galaxy, even the ones that are in the very far outskirts, are going around it at the same speed. The only way that makes sense is if all those stars are in the same small region. and they're in the small region of a much, much grander or larger object, okay? Mond, I think, was able to answer those. It's like, hey, this is what you can do instead to show it. And we were like, cool, thumbs up. But in one of the examples I showed you with the bullet cluster, the bullet cluster basically just tossed Mond out the window. It said, you can't answer Mond, you can't answer that effect by using Mond or by using modified gravitational effects. The only way it works is if you, unfortunately, you have to have the principles of dark matter. Why? Because it follows the math. We know that mass, or therefore matter, has the gravitational effect, and it makes things move. And the only way that it works to line up, the evidence has to match our observations, it has to match our math. The only way it works is if you put in dark matter. Yeah.
Well, right now, I agree with you that it is the most plausible explanation to date.
Just,
but the phrase "to date" is what I'm going to key on, because if you will, by your own arguments, admit that at one time in our history, the Earth being the center of the entire universe was the best and most logical explanation to all of this, until Copernicus came around, okay? And it's been building on that ever since. Now, I just don't feel like the dark matter, dark energy thing is it's good for right now, but it ain't correct. Not really correct.
Yes, it doesn't answer all of our questions, but it answers them the best logical way. It's known as the lambda CDM, random cold dark matter universe, right?
I have a feeling that like the Boyte's void, that is void of dark matter, but it's full of dark energy. Yes. Energy and matter, I mean, let's face it, energy and mass are basically interchangeable.
They are. Yes, sir, they are. Through E equals MC squared. You're absolutely right. And just what you said about the Boyte's void, that's one of the areas that we can find evidence that shows the universe expansion. And so what makes dark energy different is that it causes the expansion rate of our universe to increase, okay? And the way I picture this is, I don't have a baseball, right? So I'm sorry, I know I'm moving on. Let's say you throw a ball up in the air, right? So you throw the ball up and then it slows to a certain point, right? That momentary freeze, and then it falls back down.
Ballistics.
Yes, sir. And that's due to the effects of gravity, though, right? So that's showing you how gravity works. So if our universe was only consisted of gravity, right, or properties of mass, if you will, and matter, then our universe, we know it started. So what we call the Big Bang, we know there was a start, an inflation period, and then over time, our universe starts to slow down, right? That's the equivalent of the ball coming to a certain stopping point. But why we say that dark energy is there, or there is something else in our universe, is because the universe's expansion rate started expanding it again rapidly. So this is like taking that ball and it's slowing down, then all of a sudden shoots up like a rocket into the sky.
Yep.
How do you explain that, right? So you start doing math, because math is the universal language of science. And then when you look at the math, the only way you fit is you have to plug in something that says, this is what makes it work. And that's something that you plug in, that unknown variable would be dark matter, or lambda, or dark energy, excuse me. Yes, sir.
I don't want to hold this up anymore, but you and I got to go have a beer sometime, okay?
Okay. Yes, sir. So great question. Great question.
All right. I want to make sure, were we recording?
Yes. I see it at the top. It says recording still.
Okay.
Yep.
All right.
So
Any other questions? Yeah,
It's
go
got to be
ahead,
recording
Scott.
somewhere. I'm just saying that it's recorded somewhere, but it looked like, who was having a question?
Well, I was just gonna say, I don't know
if anybody had mentioned it to Mr. Greg there or not. But one of our club members that is now a professor emeritus at LSU and has now moved out to Arizona, was part of the team that what was the guy, Saul Perlmutter, yeah, that won the Nobel Prize a few years ago for discovering dark energy. And so he helped write, he was one of the authors on one of the papers, and so he got to go to Stockholm and see the ceremonies and all that kind of stuff for it.
And
So
he even bummed around with us.
Yeah. So we have heard a little bit about dark energy.
Yeah. Cool. That is super cool. Well, I count it an honor to be able to present on a subject like this. Then I really do.
It was awesome. It was great.
I move we make Greg here an honorary member of brass if he's not one already.
Absolutely. Oh, Greg, I'm a retired science teacher. I used to teach, and I would also teach teachers how to teach science. You were awesome. I can see why the kids would love you, and the adults too at the programs. Thank you.
Thank you very much. I definitely appreciate that.
Yeah, you need a YouTube channel.
Yeah, definitely.
Yeah,
but I know that Mr. Andrews here has been a fantastic speaker.
Yes, he has.
And let's give him one more round of applause to thank him for his effort tonight.
Thank you. Thank you.
Very good.
Thank you.
Okay, if there are no more questions, we can go ahead and allow him to go do his thing and spend time with his family and all that for the rest of the night. If anybody else wants to harass him, speak up now or write him, and we'll give you his email later, and y'all can go have a beer or whatever.
Yeah, I'll harass him later.
Or yeah, contact Coy, and Coy can do it in person for you. And if you get to annoy Coy too much, we'll set up a grudge match.
All right. Thanks so much, Greg.
Yeah,
Thank you.
absolutely.
Thank you.
Thank you.